Hey everyone, and welcome to this explainer. Today we're diving into the absolute fundamental building blocks of the physical world to figure out exactly how scientists categorize, well, everything around us. Have you ever wondered how a chemist looks at a rock, a glass of water, or even the atmosphere, and just instantly knows how to take it apart? Well, let's explore that hidden architecture of matter together. But before we really get going, I want you to consider a common misconception about the air filling your lungs right now. Is it a chemical compound? I mean, it kind of feels like a single, unified thing, right? We're actually going to solve this little paradox later in the explainer using a really cool property-based puzzle. All right, here's our quick roadmap for today. 1. The architecture of matter. 2. Elements, the solo acts. 3. Compounds, an identity crisis. 4. Mixtures, the roommate rule. 5. Solving the property puzzle. And finally, 6. Physical versus chemical changes. Let's jump in.
Section 1. The architecture of matter, defining the so what of material classification. To start, matter is literally anything that has mass and takes up space. But what's incredibly fascinating about this taxonomy map is how it splits all of that matter into pure substances and mixtures. Now, why does this classification matter? Well, it gives scientists the ultimate power, predictability. By identifying whether a substance is pure or mixed, they can predict physical constants. Pure substances exhibit these really sharp, definite melting and boiling points, while mixtures just don't. It's basically the ultimate cheat sheet for predicting how any substance behaves.
Moving on to Section 2. Elements, the solo acts, the basement level of chemistry. Elements represent the absolute basement level of chemistry. They are pure substances made of only one type of atom, and they absolutely cannot be broken down into simpler substances by any chemical means whatsoever. They're represented by unique symbols, like C for carbon, which amazingly manifests as both incredibly soft graphite and super hard diamond. The atom is the absolute smallest unit that retains these highly predictable properties. You can kind of think of elements as highly independent individuals that serve as the primary foundation for all complex material existence. They are powerful on their own, and they remain completely unchanged by regular chemical reactions when they're isolated. But, as we'll see in a second, the physical world gets a whole lot more interesting when these solo acts decide to meet. Which brings us to Section 3. Compounds, an identity crisis. When solo acts form permanent partnerships. When elements form a permanent chemical union, they create a compound. This basically means different elements locked together in a strictly fixed, definite ratio by mass. Think H2O for water, right? In a compound, the smallest unit of identity isn't the single atom anymore. It becomes a molecule or a formula unit. And breaking this union? Not easy. Those chemical bonds require immense energy to dismantle. So, the absolutely crucial takeaway here is that elements undergo a total transformation in personality when they chemically bond. We actually call this the chemical identity crisis. The elements completely surrender their original individual traits to adopt an entirely new collective identity. And this brilliantly illustrates that whole identity crisis concept. Look at the before state. We've got sodium, which is a wildly reactive metal, and chlorine, a literally toxic gas. If you encounter them individually, yeah, they'd be incredibly dangerous. But after they bond in a fixed ratio, they become sodium chloride. Those lethal individual ingredients combine to make table salt, something totally safe, essential for life, and frankly, delicious on your French fries. Their past identities are completely erased by the new compound. Section 4. Mixtures, the roommate rule. Navigating casual cohabitation. So, what happens when two or more substances are just physically combined? You get a mixture. Unlike compounds, they can exist in absolutely any variable proportion. There's no fixed recipe here. And because they're impure in a strict chemical sense, mixtures completely lack those sharp, definite melting or boiling points we talked about earlier. Instead, they boil or melt over a really broad range of temperatures. I love this analogy because it perfectly explains the behavior of mixtures. It's the roommate rule. The components are coexisting in the exact same space, sharing the exact same environment, but they never actually merge their chemical identities. Each component keeps all of its own quirky physical properties completely unchanged by the presence of the other stuff in the room.
Okay, let's return to our hook from the beginning. It turns out air is actually a homogeneous mixture, not a compound. And here's exactly why. First off, the recipe is variable. The air in a dense pine forest has entirely different gas concentrations than the air in a crowded city center. Second, there's no chemical union. Nitrogen and oxygen are just kind of drifting together. And third, the oxygen you breathe behaves exactly like pure oxygen because it never surrendered its personality to a chemical bond. It's just sharing the room.
This framework acts as an amazing cheat sheet for the laboratory. It summarizes the strict rules governing the three relationship statuses of matter. Notice how compounds require intense chemical methods for separation, while mixtures, because they just have variable physical ratios, can be separated using simple physical methods.
Section 5. Solving the property puzzle. Exploiting physical flaws to unmix matter.
Because these roommates keep their individual traits, we can actually pull them apart just by exploiting their physical quirks or their flaws. Got a solubility difference? Boom, use filtration. Boiling point differences? Distillation is your friend. If those boiling points are incredibly close together, you step it up to fractional distillation. And hey, if one component happens to be magnetic, just grab a magnet and pull it right out. Absolutely no high-energy chemical decomposition required. Let's actually see this in action with a classic laboratory protocol. Imagine you're handed a messy blend of salt, sand, and ammonium chloride. The sequencing here is absolute. Step 1 has to be sublimation, applying heat to make the ammonium chloride turn directly into a gas. Because think about it, if you add water first, you dissolve that chemical, destroy the shortcut, and completely ruin the process. Only after sublimation do you add water to dissolve the salt, filter out the sand, and evaporate the water to recover the pure salt. It's like a giant puzzle.
And finally, Section 6. Physical versus chemical changes, the final diagnostic case study.
This case study demonstrates the defining line in all of chemistry. If you just mix iron filings and yellow sulfur powder together on a desk, they follow the roommate rule. You can literally drag a magnet right through the pile and pull all the iron out. It's just a physical blend. But if you apply intense thermal stress, if you really heat them up, a chemical reaction occurs. They cross the line straight into an identity crisis. The iron permanently loses its magnetism, the sulfur loses its color, and they form iron 2 sulfide. It's a brand new, uniform black substance that cannot be separated by physical means ever again.
So, as you think about how to actively manipulate the diversity of the physical world, consider this. We just saw how easily we can exploit physical quirks to pull a simple mixture apart. But what does it truly take to break a permanent atomic partnership? What precise types of massive energy must we master in the lab to shatter the deep bonds of a complex chemical compound and give those elements their solo identities back? Keep that question in mind as you look at the physical world around you today. Thanks so much for joining me on this explainer, and keep exploring.